Hello everyone, welcome to the TOMlLO interview room. I'm the host Yun Yun. Today, we are honored to have with us an expert in the battery field, Senior Solution Director Xia, who will provide us with in-depth answers to some questions related to the reliability and environmental testing of battery packs. Hello Xia.
Hey, hello.
Why did we choose this theme for this episode?
Well, I learned that in our last episode, we shared information about safety testing related to battery cells, focusing on how to ensure the safety and reliability of batteries under various extreme conditions for consumers of no-energy vehicles. Apart from safety, there are other concerns as well. One is the charging speed of our batteries. How long does it take to charge the battery to over 80%? Is it half an hour or even less? Another concern is the cycle life and storage life of our batteries. After years of use, can the minimum performance of the battery still be maintained at 75% of its original level? All these issues are related to the reliability and environmental testing of our battery packs. That's why we've organized this episode sharing.
Indeed, these are all questions that our customers are very concerned about. I have a question. I noticed that the theme mentions the term battery pack. What's the difference between a battery pack and the battery cells we discussed in the last episode?
A battery pack typically consists of the following parts. Let me put it this way. Battery cells are the most basic unit of a battery pack. Just like soldiers are the basic unit of combat, a module is like a squad or platoon, organizing several soldiers together. The battery pack is a complete Army Corps. The BMS system is the general headquarters of the Army Corps, responsible for command, decision-making, and intelligence. The thermal management system is the logistics and medical unit of the Army Corps, ensuring that our soldiers are in the best possible condition. The structural enclosure is the armor and fortress for the soldiers, providing protection. The electrical system is the communication and supply lines of our Army Corps. We can get a complete understanding of the composition of our battery pack through the following picture. Therefore, the technological level of our battery packs directly determines the safety, cruising range, charging speed, cycle life, and overall performance of our electric vehicles. It is one of the most core components of no-energy vehicles.
That's a very vivid and illustrative explanation. Let's get back to the main topic. So, how can we ensure the safety and the reliability of our battery packs? What multi-dimensional tests do we need to conduct? Let's discuss this in detail.
First, let me talk about fast charging tests. Our test scenario simulates rapid energy replenishment to obtain fast charging speed data. The purpose of the test is to evaluate the charging performance of the battery. The test pass condition clearly stipulates that the fast charging time must be less than or equal to the required time. Usually examine the charging time from 10% to 80% of the battery capacity at temperatures above 0 degrees Celsius, which must be less than or equal to 30 minutes. This is also the charging time issue that everyone is concerned about.
What are the technical challenges in this test? Does TOMlLO have any unique solutions?
For high-rate fast charging, the heat generation is significant, and controlling the temperature of the battery cells is difficult, which seriously affects the test results. The basic performance parameters are sensitive to temperature, affecting the consistency and accuracy of parameter testing. During testing, we need to accurately control the surface temperature of the battery cells at the specified temperature. As much as possible, TOMlLO has multiple solutions. For example, our direct refrigerant cooling solution, with the increasing demand for 3C, 4C, 5C, and even high-rate fast charging. Direct refrigerant cooling has been adopted by more and more automotive companies and electronics manufacturers. Correspondingly, battery pack testing requires refrigerant cooling equipment to provide refrigerant circulation. Our battery pack direct refrigerant cooling machines at TOMlLO use environmentally friendly refrigerants and can adaptively adjust to changes in test conditions, reducing debugging time. Then there's the liquid cooling solution. With the increasing demand for high-rate fast charging, the temperature rise of battery cells is significant, and the temperature chamber alone can no longer control the temperature of the cells. Therefore, we have developed multi-channel chiller units to solve this problem, which can simultaneously provide circulating water to multiple cells. When the charging rate changes rapidly, we can achieve a battery surface temperature fluctuation within plus or minus 2 degrees Celsius.
To ensure the safety and the reliability of battery packs, what other conventional tests are there?
We usually conduct cycle life tests and storage life tests. The test scenario simulates long-term charging and discharging cycles. To obtain aging data, the purpose of the test is to provide aging data under various conditions for creating models, assessing lifespan, and providing warranty basis. It also serves as an object for safety research. The test pass condition requires that the health state under warranty conditions must be greater than or equal to the required health state, which means that after years of use, the minimum performance of the battery can still be maintained at 75% of its original level. The test conditions specify performing charge-discharge cycles within specific temperature and state of charge ranges every 100 cycles or every 30 minutes or every 30 days. The battery needs to be removed for short-term performance aging testing until it reaches 65% of its original health state, or after 360 days, at which point the test terminates. We can see that the pain points of this test include the following. First, the test duration is long, and maintaining a constant temperature over a long period requires frequent stops, removal, and transportation to the short-term performance testing area, necessitating frequent disassembly and assembly. Second, there is a need for frequent queuing and waiting, making it impossible to precisely control the aging time. This requires a large number of devices in the laboratory to meet simultaneous testing needs. Third, solving the queuing and waiting issue is crucial.
Having more devices means higher costs, which is not something a boss would be happy about.
It seems you're quite cost-conscious. That's right. Having a large number of devices brings several problems. First, our operating costs increase, with electricity bills being a major expense each year. Second, a large area is needed to accommodate the devices, and laboratory space may be insufficient.
So, how does TOMlLO practice the value of customer first? In these aspects, do you have any solutions?
We have a one-to-many solution for our battery pack distributed environmental chambers. Taking a 1-2-4 solution as an example, it significantly outperforms traditional solutions. During the testing process, the annual electricity savings are approximately 56,400 yuan, and the monthly savings are around 4,700 yuan. Moreover, the more units it drags, the more electricity we save.
How is this energy reduction achieved specifically?
In most operating conditions, we maintain a constant temperature using a small compressor. For a small portion of the time when cooling is needed, we use a puppet unit for assistance. This design inherently reduces energy consumption. Additionally, our self-developed control system at TOMlLO employs advanced algorithms to significantly improve the efficiency of the refrigeration system, which is also a key point for energy savings.
You mentioned the use of small compressors earlier. Since small compressors occupy less space, does this mean we have measures in place to save space as well?
Indeed, the volume of our constant temperature units is smaller than that of traditional large compressor units. Looking at the layout diagram below, we can see that, second, we adopt a double-deck walking design combined with a one-to-many approach, which can solve both the space and energy consumption issues.
This solution sounds quite practical. Are there any other highlights?
Our solution features an overall sinking design for the chamber. The bottom of the environmental chamber is flush with the floor of the experimental plant, facilitating sample handling. Second, it adopts an overall detachable structure, connected and fixed with fasteners, allowing for flexible maintenance and disassembly. Third, the top of the chamber is equipped with a slightly positive pressure smoke collection hood. When the battery loses control and the pressure relief door opens, smoke can be quickly vented.
Are there any specific practical achievements of this comprehensive solution within the industry?
We have completed transactions for around 100 units with leading companies in the industry, and we have over 100 projects in progress.
Great, it seems the prospects are very promising. Let's get back to testing-related topics. We've mentioned high-rate fast charging tests and lifespan tests, as well as our solutions. For these two tests, are there any other tests?
Currently, in the national standard GB38031, safety and reliability tests are conducted under single operating conditions. However, the actual usage scenarios of our electric vehicles involve multiple operating conditions superimposed. For coupled operating condition tests, we have 3 integrated test chambers that combine temperature, humidity, and vibration environmental stresses. Compared to single factors, they can more realistically reflect the product's adaptability to composite environmental changes during actual use. This type of test accounts for a relatively small proportion of overall battery tests, so we won't delve into it too much here. You can watch a video to get a brief understanding.
Welcome to the introduction of the large-scale 3 comprehensive test chamber. The 3 comprehensive test is a comprehensive environmental and reliability test that applies temperature, humidity, and vibration stresses to the test specimen. It serves as a critical experimental method throughout the entire process of new product development, prototype testing, and product qualification certification. The test chamber adopts a gantry structure, with the chamber body driven by an electric motor. The multi-axis lead screw linkage enables the chamber to move vertically, while the bottom part moves horizontally via a track motor, achieving movement in both vertical and horizontal directions. The movement distance and position of the environmental chamber are confirmed by contact switches, ensuring rapid positioning between the chamber and the interface plate. The environmental test chamber is connected and sealed to the vibration table through an interface plate, which is custom designed based on the requirements of the test product. The interface plate is made of silicone composite material resistant to high and low temperatures, providing excellent thermal insulation, sealing, and flexibility. It also isolates the transmission of vibration sources, ensuring long-lasting durability. The environmental chamber system supports integration with on-site control platforms and can be connected to a centralized monitoring system. It enables real-time display of temperature chamber equipment status, fire safety information, and live monitoring video footage.
The main concerns of battery pack users are charging time, cycle life, and storage life. Correspondingly, today we introduced fast charging tests, aging lifespan tests, and TOMlLO's comprehensive and advanced testing solutions. Thank you, Xia, for your detailed answers. I hope today's explanation has given everyone a deeper understanding of battery pack reliability-related content. See you in the next interview.